welcome to my talk. I've seen this is a very long afternoon session, so I hope everyone had another coffee before this. So this is in the advanced track, but it's not going to be that of an advanced talk. Although one of the big things I want you to take from this talk is how to spell quiescence. That's really the key here. So one thing, of course, you should do is rate the session. And this is going to be tough because I'm directly in parallel. There's Alex speaking, so people will compare, our two talks, I'm sure. Okay, so this talk is about concurrent programming, and the big question is, well, have we solved this problem yet? Like, is concurrent programming now super easy and everyone can do it and nobody makes any mistakes and so on? Well, I don't know, but there's a lot of promising programming models out there, right? And abstractions. And for example, monitors are great. They were so great that Sun decided to bake it into Java. We have futures and promises, which are quite widely used, obviously. Async and await is part of C#, F#, Hack, and we have it in Scala as well to simplify programming with futures. Once upon a time, software transactional memory was the best thing in the world. It didn't turn out to be that big of a deal after all. Actors, of course, have caught on quite a bit, and if you've used akka before, you've also used actors, I'm sure. Joint calculus has inspired many programming models. There are agents, CSP, which is actually quite old, and has issues with distribution, right, and so on. And we have reactive streams, and we just keep on doing these things, right? We propose new things, and the newest thing will always, make everything so much better, right? And of course, I'm also charged as guilty here because I've been working on different systems for a long time. And this list on the left is not it's not enough. I also have other more researchy projects and so on that many of which are related to concurrency. For example, flow pools is a pretty cool project. We did also with Alex Prokopets and others at EPFL on deterministic concurrency, which is actually also the topic of this talk. Then Spores is a bit more general, but also wants to make closures safer to use in a concurrent setting. So now, of course, the question is, well, why are there so many concurrent programming models? And, well, people basically have realized that it's a great way to sell consulting services, all right? And I have some track record on this as well. But, well, of course, the truth is it's just a very difficult issue, right? And because there's many things that can go wrong. We can have race conditions, deadlocks, live locks. We can violate fairness, which can lead to issues and so on, right? And in fact, there's a kind of even more fundamental issue, which is just non-determinism, which means that, and that's at the root of several of the hazards. So non-determinism can be the cause of a race condition. It can be the cause of a deadlock if we acquire locks in different orders non-deterministically, right? So it's actually a core issue. And what is non-determinism, right? And perhaps the most simple example looks a bit like this. I try to be realistic, so I have a volatile variable. And well, if we concurrently set this variable to some value, then the question is, what's the value when the method returns, right? And of course, it could be 2 or 1, for example, cannot be 0, but well, and what's the value when the future is completed? We don't know, right? And there can be many variations on this. And in this case, the value could also be 0 when the method returns. So it's that's the simplest possible way. And of course, in real code, this is can be much more hidden, right? But of course, this reordering of operations is not always an issue, right? For example, let's say we have a concurrent set. So I'm using the try map here because it's a really awesome data structure by Alex Brocopets. And I'm using it as a set, so the keys here are the values in my set. And of course, I can now concurrently add things to my set. And in this example, well, the nice thing is that at least it doesn't matter. Eventually, there will always be both values 1 and 2 in the set. So that's nice, right? I can fill up sets concurrently, and that works out pretty well. So it really depends on the data type that we're using, but not only the data type, but also the operations that we're using. So for example, our nice try map here, well, we still run into issues if we mix puts and contains, for example. Right, so because in this case, well, we concurrently put values into our set, but then if you concurrently check if the set contains 1, then this condition can non-deterministically evaluate to true or false. So that means we can't just mix operations arbitrarily, right? So even though we have a nice thread-safe data structure and so on, we still can't, it's still a non-deterministic program. All right. So now some important questions I think are, well, how do we know that we've written a deterministic concurrent program? That's a basic question, right? So and deterministic means, well, it's essentially a functional program. If we give it the same inputs, how can we know that we will get the same outputs, right? And well, the thing is that there's always essentially a possibility for Heisenbugs where, there's no race, no data race if you run this 1,000,000 times, but then maybe in run 1,000,001 there's the data race, right? And of course these things are extremely tough to debug, and even writing a good regression test can be tricky, right? So basically what we want is a simpler way to determine whether some code is actually deterministic, some simple criteria. Another important question is, well, of course we can impose very strict rules onto our code that ensure it's deterministic, right? There's certainly certain patterns. I showed you one, which is I just create a concurrent set and I only allow additions to the set. Well, that's going to be fine. That's deterministic. Eventually, the set will always contain the same values. But that's a very restricted model, right? So we still need expressivity in the programs that we can express, and while they stay deterministic, right? Because, well, draconian restrictions are not really desired. So that's the second goal, is how can we reconcile determinism and expressivity, right? And this is, well, that's the topic of ongoing research, and I'm going to give you one approach that is quite interesting for some real applications. So let's look at our approach that we do here. So what this talk is about is essentially extending futures and promises with lattice-based operations. And, well, the reason is that if we have, if the data is based on a lattice, then we have guarantees like commutativity and associativity and idempotence, which are very useful to guarantee determinism. The second thing is quiescence, right? And you're going to read this word over and over again in this talk so that you will get to know how to spell it, right? And but what's interesting about quiescence is it turns out that this is also crucial for determinism. This is actually very surprising, and I hope my examples later will show this also, why quiescence is important, and I found this very surprising, because it's not a concept that we usually deal with, right? But I think in the future we will see more APIs that use the word quiescence in them. So, and the third thing is that we want to build concurrent programs where the data dependencies are not super simple, where they can also be cyclic, and that's also partially because of our application, which is large-scale static analysis of code, and there we actually have cyclic dependencies quite often. So we were looking at ways to support those. With futures and promises, that's not really possible, right? So this actually is an increase in expressivity. And of course, the goal is to support this while also, again, still have determinism. Okay? And I'm also going to tell you a little bit about applying this model to, well, like I said, static analysis. And here we're interested in the performance, of course, but also expressivity and well, general the benefits of what we do. Okay? So this model is called reactive async, and this maybe sounds a bit funny, but it is related to reactive programming, or, well, also functional reactive programming, although what we do is not, it's not completely functional in the sense that you know, we will do updates of data, so it's not functional reactive in that sense, right? But it is asynchronous and it is reactive, so that's why this is sort of the name for now. But what we do is we use two core abstractions, and it's analogous to futures and promises. We have one abstraction called cells, a cell which is similar to a future. So it's an interface to read a value that's asynchronously computed. And the cell completer is like a promise. It's a way to complete a cell with a value. And but these are, right, so we can think of cells extending futures and cell completers extending promises, although this is in quotation marks, so this is in the implementation, it's not actually done this way. Yeah, we'll see. But what's very special is that the value that these cells and cell completers contain, they must be taken from a lattice. So there must be a type class instance for a lattice, okay? And I'll give you several examples if you don't remember your discrete math. Okay, but what the purpose is that we can do monotonic updates to cells. So in contrast to futures, which we can complete only once, in this case we can actually monotonically grow the value that's contained in a cell. Can be very useful. Okay, so let me give you an example. So let's say we have a social graph, right? And it's a vertex is a user, and we want to traverse the graph and collect IDs of interesting users, right? So let's say they want to find all the users that seem to be supporters of Bernie Sanders, and we want to figure out if we can sway them to support Clinton with a mass emailing or something like that. And of course, the graph is going to be large, so we need to do this traversal concurrently. Okay. So what we can do with these cells is basically to say, okay, we just collect all the IDs in a cell, And so the cell will contain a set of IDs, right, or a set of integers. And the only requirement that we have here is that that we have a lattice, right? And but that's okay because mathematics tells us that the subset of a set, or all the subsets of a set, form a lattice, right? So in particular, if the cell only contains a set of integers, well, that's an element of a lattice of all the subsets of integers, of all the integers. Okay, so we're fine with that. And so how does this look like? And I'm simplifying slightly here, because I'm going to show you certain aspects of this model later on. So we're building this step by step. But what we do is we need to first create a cell completer, because we want to put IDs as we find them into the cell. And we say, well, this contains a set of int, all right? And now we need to have a lattice instance, right? Because the cell completer will not let us create, so we cannot create a cell completer unless there is an implicit of type lattice of set of int, right? And so this is what we do here. We just provide a very simple instance, an implicit object, which implements the lattice trait here, and this has just two members, empty, which is, well, the least element of the lattice, so it's just the empty set. This is what we start with. So when we create a cell, we start with contains an empty set, basically, and then we need to implement the join operation, which is fundamental. So if we join just says, well, how do you merge two values, right? Two sets of ints, how do you merge them? And well, we just compute the union of them, right? So that's the lattice, and in fact, this is more precisely a bounded join semi-lattice, and it's bounded because it has a least element here, and it's join semi-lattice because we're only interested in joins, not in meets. So we don't compute the meet. We only ever grow things here. Okay, and so now if we have such a cell completer, user IDs, we can put sets into it as we find them. So let's say we find the user ID, then we just create a set that contains that, and we call put next to put it into the cell. And what this does is it will take the current value that's in our cell and compute the join of the current value with this with the argument of put next. Right, so we just compute the join so that we have both the old set plus the new set. Right, very simple. We just add it to the set. Okay, so this is not very different from having a concurrent hash set and just adding things concurrently, right? But this is a bit more general because we can have. Well, I'll tell you later why this is more general and what else you can do with it. Okay. All right, so now the question is, well, once we've done this whole traversal, how can we read the result and work with it, work with all the users we found? And well, the issue is if you do such a thing and you have a large graph, then this is not really a data parallel operation where you know when you're done. The problem is that you have lots of concurrent activities, and this is not limited to this example. This is in other examples you have the same problem, that you have lots of concurrent activity going on, and in this case we don't know when this value is not going to change anymore, when the value of our cell is not going to change anymore. Basically, you know, there could still be ongoing concurrent activities, so there could be some subgraph that is still being traversed. Of course, you could think that, well, okay, let's use some sort of latches and things like that, or use an actor that you notify things. But that can be very error-prone. And also, once you do that, you run into the issue that you can still introduce things like deadlocks and other things. So this manual synchronization, well, again, you go back to the problem of how can I make sure that what I'm doing is correct, and it's not going to suddenly stop if I have a large enough graph. Okay? So the solution is actually, well, that's actually the wrong word, so sorry about that. It's actually, the opposite is quiescence, of course. So quiescence means that, well, what does quiescence mean? It means a situation where the values of the cells are guaranteed not to change anymore, right? And so what we want to do is we want to check that there are no concurrent activities ongoing or scheduled, right? They may not have been started, but they might be scheduled, that could still change the value, okay? And we don't want to manage this explicitly, but we rather want to give this as a task to our thread pool. So the thread pool should detect the situation, right? Because the thread pool knows, well, which tasks are ongoing, which tasks have been scheduled, right? And so now how does this help us? Well, let's revisit the example. What we do is now we extend the API. So instead of just having cells and cell completers, we also use what we call a handler pool. So that's essentially, that's like an execution context that you use for futures, except that in this case, there's some API that we need to use explicitly, so it's not all implicit, and I'll show you why. And this has to be associated with the cell completer. And now we can again traverse our graph, put user IDs into the cell. But when we want to read the result, we say, well, we register a onquiescent handler, right? So we say pool.onquiescent of some cell. So the cell completer has a cell associated with it. So this is like with a promise. Each promise has a future associated, right? So what we do is we say, well, once the pool is quiescent, please read the value that's in this cell, the cell corresponding to this completer, and here we have a closure to work with the collected IDs. Okay, and so the nice thing is that when this is triggered once we know the entire concurrent traversal is for sure finished, right? And the cool thing is there are no barriers or anything like that in this code. Okay, and of course afterwards, we can again launch additional like follow-up computations, right? But we have so we can structure our computation in phases, right? Where we do a phase which goes completely crazy, lots of concurrent activity, and then we say, okay, well now let's just wait until we're quiescent. And then we have deterministic results that we can read from the cells, work with them, and then we can spawn off a new phase that again spawns lots of concurrent activity. Okay. So and this is safe, and like the important bit is that this is still all deterministic, right? That's the key thing. Is safe means that we know the values are not going to change. And because we use lattices, the cells will always have the same values in them once we reach this point. All right, so let's talk a little bit more about handler pools, what they are. So it's essentially an execution context with certain extensions. One is this event-driven quiescence API, where I showed you one method on quiescent, right? We can also, or the pool is also critical to resolve, for resolving dependencies between cells. And that's another thing that I want to talk about next, which gains some expressivity also with respect to futures. So basically, this whole dependency issue is related to data flow, concurrent data flow, and just like futures, with cells, we have a non-blocking interface, right? Where we have on the lowest level, we have callbacks that get invoked once a cell receives an update, for example, right? And on top of those callbacks, we can create high-level combinators, just like with futures, right? We can have typed combinators like map and filter and so forth. And so one important purpose is to actually express some kind of data flow, right? Concurrent data flow through our application. And if we go back to futures, then if you've used futures before with the combinators, then this looks familiar, right? You have a future, you call map, pass a function, filter with a predicate, and so on, right? So this is not cells, this is just plain futures here. And if you think, you can think of this as creating a data flow graph, right? Where you start with a future, and this here is a map operation with fun, which results in a future prime, which is not shown here, right? That's the result of map, and here is filter with predicate, and the result is some future prime prime. Okay, so this is how we build data flow graphs, and the same is true for cells. We can do the same thing, and now the question is, well, what if my data flow graph has cycles? Yeah, so with futures, we can't actually express cycles. They're not going to be resolved, right? There is going to be a point where things just stop and we can't resolve them. But with cells, we can actually deal with them. So let me first give you an example for when data flow graphs can have cycles. And the example I want to take from our main application that I'm going to show you later, which is static analysis of JVM bytecode. So what we want to do here is, for example, determine the purity of methods. Yeah? So we're given some class files, and we want to figure out, well, which of the methods are pure. And so we have a bunch of rules that say, for example, well, a method is impure if it accesses a non-final field, or a method is impure if it calls another impure method, and so on, right? So we have a collection of rules that we check, that the static analysis checks. And if a method cannot be determined as being impure, well, then of course it should be marked as pure. If there's no rule that tells us that it must be impure, then the method, we can safely say it's pure. And so we can visualize the dependencies between methods very easily. So method A depends on B if it calls B, right? Because the purity of A depends on the purity of B. So if B is impure and A calls B, well then A is also impure, at least according to this purity analysis. And well, of course, B can call C, right? So that if C is impure, then B is impure, and so on. And of course, we can have a cycle as well, right? And so they can all depend on each other. And moreover, it may even be the case that we do concurrent analysis, right? And at some point, our pool is quiescent, and there are still cells where we have not determined whether they are pure or not, right? So there are still methods where we don't know whether they're pure or not, right? And by the way, each method has a cell which tells, okay, is that method pure or not, right? And so we may have this cycle where we say, well, we know that A calls B, B calls C, C calls A, but that's all we know, and there's no rule that tells us that any one of these is impure, right? So then what do we do? Well, the idea is that we kind of use resolution policies that we can plug in, and they can actually be very simple. So, and I think they typically are simple, at least in our applications, where basically in the purity analysis we say, well, if we have such a cycle, right, then all of these cells, they should be resolved to pure, because there's no rule that was triggered to make any one of these methods impure, right? So, and with cells, we can express exactly this kind of resolution, these resolution policies. So the way this looks like is actually the second type parameter that I haven't talked about so far. And this API is still subject to tweaks and so on. So, don't take this all too literally, but what we do is basically have something called a key for now, which says, well, okay, we have a lattice, which is the purity lattice. And the purity lattice just says, well, we have unknown purity, and from that we can do a monotonic update either to pure or impure, and that's basically it. And then we have a top element, which is reached if we have actually conflicting information, right? So if we update to pure and then later on we update to impure, that would go to the top element of the lattice, which indicates a failure, essentially. So just like with promises, you can complete them with a failure. You can also complete a cell with a failure that way. Right, so we have this is our lattice, purity. It's a very simple lattice. There are not many elements in it, right? But what we also specify is this key, and the key tells us how to resolve cycles, right? And this method simply says, well, given a collection of cells, how should these be resolved once we have this cycle? And this doesn't have to be a cycle. In fact, it's a strongly connected component, right? Because in general, we can have graphs that look like that, where a strongly connected component says every vertex is reachable from every other vertex, right? And in this case, the resolution strategy is super simple. We just say, well, each cell should be resolved to pure. So pure is an element from the purity lattice, right? So that's basically what we do here. And again, and this is what the cell model provides, is basically it says, well, you can wait for quiescence, and I'm going to show you this concrete example later. You can wait for quiescence, and when you're quiescent, it will check, well, are there any strongly connected components that are unresolved, right? And if they are, then we're going to apply the strategy that you've specified. Okay, so basically, in the purity analysis, what we do is it's actually rather straightforward. So let's say we look at all the class files in our project and all the methods. We create a cell completer for each method, right? And this needs a pool that we've created before, a handler pool. And we have this purity key, which tells us how to resolve cycles, right? And then we will simply, spawn the concurrent analysis of all these different methods. So they will all concurrently be analyzed. And during the analysis of a method, we may have to wait until we know the result of analyzing a method that is being called, right? So we have all these dependencies between these cells and cell completers, right? And then, but what we do at the end is we say, well, okay, let's wait for quiescence, right? And we not only do that, so we're actually not waiting. Instead, we get a future, and this future is completed once the pool is quiescent, and we've also done resolution, right? So we wait until the pool is quiescent, and then this method will then also say, okay, let's look at all the cells and check if there are any cyclic dependencies that have not been resolved yet, and then apply the strategy, like in this case, this specified by that key. Okay, and once all of that is done, we have this future is completed. Okay, so of course, what I haven't shown you is this analyze method, which is where all the complicated analysis takes place, right? But this is how we deal with the overall setup. Okay, so let's have a look at some results, right? Because we actually applied this to, like I said, analyzing JVM bytecode, and there's a new framework called Opal, which is written in Scala, which is actually a completely from scratch implementation of bytecode toolkit, quite extensible and whatnot, quite flexible. It's also fully concurrent. It's a fully concurrent framework. What we did was, and well, here you can check it out. This is actually not my project, but I've worked with the people who did this. And what we did was we rewrote some of the analyses, right? So purity analysis that I've showed you, also immutability analysis, so to check whether a class is immutable, for example. And we ran this on JDK 8, right, on rt.jar. So this has lots of classes and methods, right? So this has like more than 150,000 methods and so on, right? So it's quite a huge static analysis task. And what we have some interesting results, okay? The disclaimer is that we haven't fully optimized our implementation yet, but we have some interesting numbers. This is on a small machine. This is like a 2 or 4 core machine, something like that. Nothing special. We're gonna run this on a much larger machine this week and so on, right? So this is quite fresh from the printing press, actually. So the thing is that this is the Opal implementation before using cells. And so for immutability, for example, to analyze the whole JDK 8 takes like 3.3 seconds. And with reactive async, this is faster. It's like 15% faster. And I think we will be able to make this significantly faster as well once we start looking really into making things more efficient and so on. But this is quite nice, but this is not the only thing why I'm excited about this, because one of the reasons why it's really interesting is that the code size of the analyses was cut down by a factor of 2. So, and that's nice because we compare Scala with Scala code, right? And Michael Eichberg is the main author of Opal. He has lots of Scala experience too. So the Scala code he writes is quite good. And we still could reduce the code size of each analysis by at least a factor of 2. And it's not less readable or anything like that. And plus, we can actually be confident that the new analyses are actually deterministic, right? So I think this is 2 strong points here, coupled with actually a faster analysis, right? So I think this is promising, but we still need we still want to do some more, get some more experience on this. So there's quite a bit of ongoing and future work. Of course, we need to look more into benchmarking and optimization. Then determinism. Right now, basically, we can tell you your code is deterministic if you use the API correctly. I mean, if you stick to the API that we provide that's deterministic, like put next and on quiescent and so on, quiescent resolve cells and things like that, then you can be sure it's deterministic. But it's not checked by the compiler that you do that. You can still do crazy stuff. So you can still do, like, in the on-quiescent handler, you could still, do a side effect to some other thing, or mix it with other concurrency abstractions. So we don't check for that. So the idea is that in the future, we actually want to do effect checking, so that determinism is an effect, or rather, rather that the effect system can tell you, do you have the capability to do something that's not deterministic? And right, and so this is something that would be really cool to look into in the context of effects in Dotty, right? And then, of course, the other question is, well, just like async await simplifies programming with futures, could there be analogous support that simplifies working with cells? Okay, so I think we're ready to conclude so that there's also some time for questions. So what I've showed you is kind of a new concurrent programming model. I should also say that this is heavily inspired by LVars in Haskell, which is quite recent. So that's just within the last couple of years, a project in Haskell. But as we know, Haskell is a very different language from Scala. So this is, in fact, not actually just a re-implementation of the model. It's quite different from the Haskell solution. And, well, the key idea is to combine lattices and quiescence to get something that allows you to write deterministic concurrent programs, support cyclic dependencies, which is crucial, at least for the applications that we've used it for so far. I think the preliminary results are quite promising. And yeah, so future work is sort of static checking of determinism. And you can check it out, fork it, and so on. It's still, like I said, the API is still a bit in flux. So there's no 1.0 release or anything close to that. Okay, then thanks for your attention, and I'm happy to take questions.
Thank you. Out of maybe because of my ignorance, but what is it I can accomplish using this instead of using an observable sequence, a reactive sequence, where the values come in and then I collect them in a set, instead of using a lattice and waiting for quiescence?
Okay, so so what's the advantage? Well, it's hard to say in general. Of course, so it really depends on what your requirements are. I mean, like if you don't have, let's say, cyclic dependencies, right? Then maybe you don't need the power of this, but you're fine with maybe a stream-based solution or something like that, for sure. But also, I mean, quiescence is good if you want to wait for a complex computation to actually, eventually terminate, right? If you have streams, then sometimes you don't actually terminate ever, maybe, right? You just have incoming events or values, and you process them as they come in, and they go through some kind of pipeline and something like that. Then, of course, stream-based system could be more appropriate. So this is really this is essentially what this is for is concurrent fixed point computations, right? Where you actually, so a fixed point computation is a computation where you compute results, and they can trigger the computation of other concurrent computations, and you don't actually know when you're finished. Right, so and this is really powerful because you can just keep the computation running and trigger, like updates trigger other computations and updates, and then you can just say, well, just do this until you're quiescent, and that means you have reached a fixed point because nothing's changing anymore. So of course, if you don't have this requirement, then maybe a less powerful solution is maybe even better, because well, as we heard in Martin's keynote, the principle of least power is probably good to yeah. Yeah.
You talked about quiescence very much in, well, as you say there, is a batch mode kind of property. You have a batch of computation that will eventually finish. and you wait for quiescence. Is there any value in maybe a weaker notion of quiescence for an online computation kind of case? Can you define quiescence for a data set with respect to some set of tasks? Have you looked at that at all?
It's a very good question. So far I haven't really looked into this really, so I don't know. But one thing that I think could be interesting is this idea of having phases, right? Where you have one phase that where you do lots of concurrent things, and you come to a quiescent point, and then you start the next phase. And this is a little bit related to things like Spark streaming or so, right? Where you have batches that are, you have a stream, but you still package things up in batches, and then you process those batches, and then you move on to the next ones. So maybe something analogous could be used, actually, right? But I haven't looked into this concretely.
Yes, two things. I guess, from my understanding, the lattice is not proven to be a lattice. It's something I say. So let's say we had the lattice defined for adding things to a double counter. Rounding errors wouldn't be deterministic. That's just a clarification. I guess that's just, we say it's a lattice, and that's how it's deterministic, right?
Yeah, that's right. There's no checking there's no checking whether it's actually a lattice. You just say that, yeah.
So the other thing is just an observation. Quiescence, I think one example of that would be a user interface where you have changes that you wouldn't really want to redraw because it's not finished, it's not stable.
Right.
When you come to quiescence phase, you redraw the whole thing.
Correct.
And then that might start a new thing.
Yeah.
So quiescence would be some kind of stage where you are conformant to some requirements, where you are consistent. Correct. Or in other applications, you are in some consistent state, and you can generate a side effect.
Right.
Send an invoice, or print a price value or something.
Correct. So that's a very good observation, right? So this could be used for things like user interfaces, or where there's a change which triggers updates, and you want that all of these updates, they should all be done, and that's, again, quiescent. So when things are quiescent, then the nice thing is, right, where I showed you this on quiescent, what you get when you reach that point is typically an immutable data structure that you've collected in your cell. And that's nice, because it's an immutable thing which you can then process with it. It's not going to change anymore, right? Then you have a handle on the result, and you can then process that further. Yep. Great. Any more questions, or?
What if the join method is not commutative?
What if the join method is not commutative? Well, then you have not defined a lattice. Then it's not correct. But I think so. So the thing is, with the lattices, I think you should look at these similar to CRDTs, right? Conflict-free replicated data types. If someone knows about these, very interesting. It's for distributed computing. But this is very much related to lattices, because there also you want operations to have certain properties like commutativity. And I think that the idea is that there will be libraries of lattices, right? And you just pick one, right? And the person who defined it made sure it's a lattice, actually, and yeah.
Just a simple question. What requirement for lattice gives you over commutative monoid, for example, abelian monoid? Why it can't serve the role of the lattice?
Well, okay, so I mean, of course, you could base the lattice onto other abstractions, right? I mean, it doesn't really matter. I mean, as long as what you define ends up being a lattice, that's fine, right? So that's not really, the model doesn't restrict you there, except for maybe the API, right, which is specific, but maybe yeah, again, I mean, lattice is not used that much, but this should probably be some standard interface, right? There's one more question in the back.
Is it on? Oh, thank you. So I think it's a little bit on the line of with previous questions, but which are exactly the properties, the algebraic properties of the lattice that you will need to do? I mean, I understand that the idea is that these cells, the value of the cells, are somehow being computed incrementally. Am I right?
Yes, you're right. So
so the idea is that the basic order will be about the order, the partial order in the lattice is whether there are more results or less, or whether the result is more or less compute, right?
Say that again. I didn't fully understand what you were saying.
A lattice is a kind of an order, a partial order over an element. And in this case, the set of elements will be the possible result, or
correct
possible results, and the order will be whether they are more, they contain more results. That was in the example you mentioned, the subset.
Correct.
The subset order between the power set lattice.
Right.
So in this case, which are the properties that you will need? The idea is that you said that this is about getting to a fixed point through the monotonic function monotonic on this lattice.
Yes.
Okay. So so what you're saying is that if you just have any monotonic function in the lattice, it will eventually reach a fixed point.
Correct.
You can assume, at least in the values. But one thing is knowing that it reaches a fixed point, but when you have the implementation of this cell, how do you know that it's already reached that fixed point?
Well, that's what quiescence tells you, right? That's how you can tell whether you've reached a fixed point, because there are no changes being done anymore. There cannot be any changes anymore.
So every data is being computed over a fixed set of the data.
Right.
So a fixed set of the
right.
inputs.
So you know the data is not going to change anymore, and also you don't have cycles that haven't been resolved yet.
Okay. And for the cycles, the solution for the cycles, if you want to get a sort of collective quiescence of the whole of all the cells in the set, right?
Yeah. Right.
Okay.
Right. Exactly.
Thank you very much.
Yeah. Thanks. All right. I think we're out of time. So thanks a lot for.